Sciences Icfas 2020, University Technology Petronas. Today, I would like to welcome all the audiences and presenters to this session. And we have today we have 5 presenters for this session. And first of all, before that, let's have this welcoming remarks from the chair.
Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera, good afternoon and good days. It is a pleasure to welcome respected speakers, delegate and participant to the International Conference on Fundamental and Applied Sciences or Icfas 2020, organized by UTP Fundamental and Applied Sciences Department with the theme of Innovative Science Towards Sustainability and Industrial Revolution 4.0, and the aims is to bring together leading experts, scientific communities, and industrialists working in the field of applied science and mathematics from all over the world to share the most recent development and cutting-edge discovery addressing sustainability and industrial revolution 4.0 in the field. We have with us 3 prominent plenary speakers. The first is Prof. Dr. Said Musa Negib, a prominent professor from British Kazakh University, KBTU, Kazakhstan, who will be discussing on from research ideas to commercialization. We will also have with us Yang Berbahagia Datuk Seri Dr. Muhammad Uzair Mahidin, prominent chief statistician from the Department of Statistics Malaysia, who will be talking on empowering innovation towards IR 4.0 DOSM experience. Finally, we will have with us prominent physicist Datuk Professor Dr. Haris bin Ahmad from University Malaya, who will be talking about pulse generation in fiber lasers in the S plus S band region. I am also taking this opportunity to express my sincere gratitude to all our respected plenary speakers, Prof. Dr. Said Musa Negib from British Kazakh University, Kazakhstan, Yang Berbahagia Datuk Seri Dr. Muhammad Uzair Mahidin, Chief Statistician from Department of Statistics Malaysia, and Datuk Professor Dr. Haris bin Ahmad from University Malaya. Thank you all for the great support given to Icfas 2020. I also would like to convey my sincere appreciation to all delegates for supporting Icfas 2020. Our delegates among all are from Malaysia, Kazakhstan, Indonesia, Vietnam, Pakistan, and Nigeria, and will be sharing their expertise in the area of sustainable chemistry, nano and sustainable technology, mathematical and analytical methods in science and technology. Last but not least, I would like also to convey my sincere appreciation to the organizing committee for Icfas 2020 and ISCON 2020 main committee for working so hard to make this conference become reality. Dear delegates, please explore our conferences. Among others are having the following features in the virtual ISCON 2020, such as virtual exhibition booth and interaction with exhibitors. And we also have resource gallery. You may download all the materials that have been uploaded. You may also go for virtual tour so that you get to know UTP better. We have also live support. Feel free to ask and seek clarification. And finally, we have also gamification. Be proactive, especially to gain more points. I hope this conference, all of you will be able to forge connection, strengthen network, gain benefit from the conference, and be part of one of the largest conference in the world and have an enriching, edifying time in ESCON 2020. Thank you.
Okay, thank you, Associate Professor Dr. Hanita. So first, we would like to introduce our first presenter, Mr. Surajuddin Sikiru from University Technology Petronas, and his title of presentation is Application of ANN Model in sandstone reservoir using parameter for predicting recovery factor. And please, audiences, if you have any question, please type your question in the Q&A chat, the live this Q&A live box. Okay, throughout the presentation, and we will after his presentation we will have 5 minutes of Q&A session. Okay, thank you. Okay, please welcome Mr. Sikiru.
Good afternoon, everybody. The chairman of the conference, the moderators, all professors here present, all dignitaries from different universities, my co-participants, I say good afternoon to you all. My name is Sikiru Suragidin Olalekon. I'm a PhD student from University Technology Petronas, Malaysia. I'm here to share with you my research update on the application of artificial neural network model in sandstone reservoir using electromagnetic parameters for predicting recovery factors, presented on International Conference on Fundamental and Applied Science, Icfas. Introductions. Most of the current world oil productions come from mature fields. Improving the recovery of the oil from the mature reserve is a major concern for the oil companies and authorities. Moreover, finding alternatives for the production the oil from discovery has been diminishing slowly in the last eras. Hence, increase in the recovery factor from the mature field under the primary and secondary production will be critical to meet the growing demand of energy in the coming years. Most of the countries have been bidding to maximize the influence of their domestic reserve for the total supply, as the major primary focus is to improve the performance of the existing field in the country by using the enhanced oil recovery techniques in a technical way. To access the reserve, they were highly inaccessible due to the geological problem or high expenses for the EOR, which is majorly concerned with the mobility of the oil through the process of drilling. This is done through the injection of external electric fluid to the reservoir. This figure 1 shows the schematic diagram of charge interface between the solids and liquid interface region under the reservoir conditions. And this shows the electric double layer of a reservoir sandstone which have the stem and diffuse layers. And there is imbalance of ions on this reservoir sandstone in which it has to be migrated from the diffuse to migrated from the stem layers to the diffuse layer so that it can be a polarizations within the environment to reduce the surface tension which lead to decrease in the interfacial tension of the reservoir. When there is external electric field, the reservoir property will be altered. These reservoir properties are wettability, viscosity, contact angle, capillary pressure, interfacial tensions, and we are majorly in this reserve. Our major concern is to reduce interfacial tension of the oil, which says that the force between the surface and the radius of the pore and the curvature of the oil have to be changed to make sure that there is a sweep efficiency in between the reservoir sandstone. This figure 2 shows the illustration of interfacial tension in reservoir in the sandstone reservoir, which shows the oil, water, which are stacked in between the reservoir pore, and at this point there should be detachment of the oil from the reservoir using external mechanism to detach this oil from this reservoir sandstone. As we all know that the reservoir rock always bear an electric potential in the presence of reservoir fluid or any other fluid, which cause the separation of negative and positive ions, which is known in the brine solutions. And also the surface property of the colloid hydrocarbon reservoir absorb more negative ions than the positive ions, and the ionic solution on the electric field which attract the positive ions to the vicinity of the negative charged surface, which will cause the polarizations with the polarization mechanism within reservoir sandstone. At this point, there will be different mechanisms that will happen in this when there is a attraction of the positive ion to the negative charge, which can cause the polarization or interfacial polarization, dipolar polarization, electronic polarizations, or ionic polarizations. And figure 3 shows the schematic diagram of artificial neural network model. We show the input signal and the hidden layers and also the output. As has been defined, that artificial neural network is usually simply called the neural network, a computing system vaguely implied by the biological neural network that constitute animal brains. And based on the collection of the connected unit or node called artificial neural network, which loosely modeled the neuron is biological brain, we'll be using the artificial neural network to model the electromagnetic parameters in this research. And I'm here to present the methodology of this research to you, which shows which shows the figure flow, the flow chart of experimental procedure, which says that from the start we use the 5 different sandstone reservoir sandstone. We use it to replicate the reservoir environment using better sandstone, and we saturated with NaCl electrolyte at different concentrations, and also the oil and the oil which we use we use the reservoir conditions to made our sandstone to prepare our sandstone. After that, we proceed to the electromagnetic characterization, which we determine the real and imaginary permittivity, real and imaginary permeability of the reservoir. And also we use SR drip to analyze the elemental composition on the reservoir stone, at least to know the type of minerals present on the sandstone. And we use SPSS analysis to define different dictates of the reservoir sandstone, and deep neural network model was used to determine the recovery factor of the reservoir. And this figure 5 showed our the developed model of artificial neural network for this research, which shows the 5 input parameters and 7 hidden layers and 1 output. And as you have been saying, that our input are the permeability, permittivity, imaginary permittivity, permeability, imaginary permeability, and reflection loss. And our hidden layer is the reservoir porosity, reservoir permeability, reservoir oil viscosity, reservoir density, reservoir pressure, reservoir temperature, and reservoir density. And figure C shows the network analyzer used for the electromagnetic parameter computation, and also the figure 7 shows the reservoir sandstone, which after the saturated and it has been cut into chip for the electromagnetic propagations. I would like to share with you the result and discussion of this research. And figure A show the SRD spectra of the reservoir sandstone, and figure 8B show the FTR analysis of the reservoir sandstone using different concentration of electrolyte, saturated at different concentration of electrolyte. It was referred from the SRD that the major minerals present on the reservoir sandstone are the quartz, the quinolite, and the chloroform, which shows that the quartz dominated the reservoir on a reservoir sandstone, followed by the quinolite, which are the major component of the sandstone reservoir. And for the fact that the percentage of different minerals and their chemical compositions respectively. And from the SRD, we're able to show that the quartz and the major minerals and major mineral present, and the feldspar are also the one of the major mineral present on the sandstone, followed by other minerals. And from the FTR analysis, it was majorly shows that the sandstone is present on aromatic carboxylic bond and aliphatic carboxylic bond, which shows that the effect of the increase in electrolyte concentrations affect the reservoir properties, which change the thickness of the reservoir due to influence of electromagnetics, and also the increase in concentration of the ions, which change the entire property and the ionic properties of the reservoir, and which are able to show that the pore of the reservoir are majorly change the ion surface and the ion interactions due to change the thickness of electric double layer. And at this point, it will refers that the there is a detachment of the oil from the sandstone, which reduce the surface tensions and also reduce the interfacial tension of the reservoir, which shows there is a easy movement of oil mobility or the fluid fluid generally from the reservoir, from the injection well to the production well. And from the FTIRR, it also shows that from the 2000 to 2700 to 3000 is for aliphatic functions, and from 1000 to 1500 CMK is from the aromatic, and from 6 to 800 is belong to the SIO and OH group. And this figure 9 present the SPS analysis, which are basically used to refer the the carboxylic group and the OH group, which is the different saturated of NaCl electrolyte concentrations, and we saw the spectra of this each ion on the sandstone. And it was evident from the result that the sandstone primarily contain the silica, and small amount of calcium, magnesium, iron, potassium, and aluminum are present, which are also presented in table 1. And however, the carbonate that present contains substantial amount of silica, magnesium, potassium, calcium, and the SPA characteristics also further validate the result obtained from the SRD analysis, which shows that due to the increase and influx of this ion, there is a separation of ion which aggregated to the polarization within the reservoir, which reduces the surface tension and also reduce affinity between the oil and the water. And this figure 10 shows the result of the artificial neural network model, and table 2 shows the SPS analysis for saturation sandstone and different NSA electrolyte. And from the ANN prediction, it was so that for the predicted value, the R square is equal to 0.994, and for the predicted value we have 0.892, which evidence that our result is more accurate. And from the it was shows that the artificial neural network develop using the equation adopted by 60% data set for the training and 40% for the text, and adds 5 input and 7 hidden layers with 244 neurons. And from our results, we were able to detect that the predictive model developed and evaluate the typical electromagnetic parameters at the reservoir sandstone and appear to be more informative than the traditional approach. And conclusions: the absorption of the saturated upon the two negative charge absorbent decrease as a concentration of the divalent ion, that is Na plus, increase in the formation of the electrolyte when saturated in the sandstone using reservoir environment condition. And this research, we were able to present DNA model for the prediction of recovery factor using electromagnetic parameter based on the fluid reservoir rock and fluid properties. And our study made use of 5 input parameters using 7 hidden layers and 1 output, and the output layer are generated from the NSA electrolyte concentrated from the electromagnetic parameter feed. And from our result, it referred that the result obtained, the model successfully predicted 70% accuracy, and our estimated of the R square of 0.994 and predicted value of 0.894, so that the techniques can be used to predict the performance of the oil recovery. Uh, and predicted value of 0.894, so that the techniques can be used to predict the performance of the oil recovery. Uh,
Okay, thank you, Mr. Sikiru. And
yes, sir.
seems like there's no question from the live Q&A. So thanks again,
Okay.
Mr. Sikiru, for his presentation. All right, so we will welcome another presenter, who is Mr. Bashir Abubakar from UTP. And his title of presentation is Temperature Conductivity Relationship of Solid Polymer Electrolyte Membrane Based on PVA K2CO3. All right, let's welcome Mr. Bashir. So please don't forget to type your question at this live Q&A chat box if you throughout the presentation. Thank you. would like to welcome Mr. Farman Ullah to present his title of presentation, which is a flexible photoelectric based on binder-free paste for dye synthesized cell. So let's welcome Mr. Farman. So please type your question at this live Q&A throughout the presentation. Thank you.
Thank you, sir.
Hello and Assalamu alaikum. A very good day to all of you respectable participants. I am Salmanullah, PhD candidate in Fundamental and Applied Science Department, University Technology Petronas, UTP, Malaysia. For today's session, I will be presenting our article entitled is Hubbard's Modified Density Functional Theory Calculation for the Electronic Structure and Optical Properties of Carbon Dioxide Anatase TiO2. Presentation outlined. We will give a brief research background for our research work. Then we will discuss hydrogen energy production methods, semiconductor photocatalysts used for hydrogen production. We will give a brief problem statement related with semiconductor photocatalysts. Our research objective for the current research work, density functional theory, DFT calculation, computational methodology of the research work, and results and discussion along with conclusions. Research background. Modern world is facing two major problems related with energy crisis and climate change. Currently, our energy resources are mainly fossil fuels dependent, about which the main concerns are depletion of these energy resources. This will affect our economy and industry also. On the other hand, large amount of CO2 emission is resulting in global warming, air pollution, heavy and unexpected raining, and thunderstorming. Solution to both these problems is the development of clean and green sustainable energy resources that include hydropower, wind energy, solar energy, and biomass energy. Solar hydrogen production through water splitting technology is also assumed a clean and green energy technology. Hydrogen energy. Why we prefer hydrogen energy? So hydrogen energy is preferred due to the following some reasons. No greenhouse gases emission during combustion of hydrogen. Hydrogen has also high calorific value per mass unit and most abundant element that can be obtained from a broad range of substances. However, hydrogen production mainly involve fossil fuels. This pie chart represents that almost 90% techniques involve fossil fuels like steam forming. 48% of hydrogen is produced through steam reforming, 30% through oil, chemical, industrial of gases, and 18% through coal gasification. Therefore, solar hydrogen production through photocatalytic water splitting technology is a tremendous idea. Different photocatalysts introduced in order to produce hydrogen production. So for semiconductor photocatalyst, there are some requirement to be an efficient semiconductor photocatalyst. The main requirements are the material should have suitable band gap that is in the range of 1.28 to 2.822 electron volt. The material should have suitable band edge position, should have frequent transfer of photogenerated charge carriers, chemically and thermally should be stable in electrolyte. The material should also be inexpensive, abundantly available, and the most important, it should be environmentally friendly. Extended research work has been truly carried out. So titanium dioxide is most widely used photocatalyst because of their stability, optoelectronic properties, low cost, and non-toxicity. However, TiO2 photocatalyst also has some limitation. The main issue with TiO2 photocatalyst is their low photoconversion or solar to hydrogen efficiency. The following are the some of the problems with TiO2: wide band gap, due to which it absorbs only ultraviolet radiation, that is just 3 to 5% of the total spectrum. So the smaller number of absorbed photon will result in lower efficiency. Second problem is rapid recombination of photo-generated electron hole pair, due to which the presence of defect site and photo-generated electron hole pair thus recombines quickly to reduce the efficiency. Also, we have with TiO2 slow reaction rates problem. The water splitting reaction has very slow kinetics at the surface of photocatalyst due to the less effective surface area and smaller number of surface active sites of the redox reaction. So, for the current research work, the objective are to design a theoretical model of carbon doped anatized TiO2 photocatalyst with an improved visible light absorption by reducing the wide band gap energy. So for this purpose, we have designed a computational model for anatase TiO2 2x2x1 supercell using first principle DFT calculation. Then we incorporate carbon impurities into the designed TiO2 supercell model with different doping concentration, and then study the effect of carbon doping on the structural, electronic and optical properties of the designed undoped and carbon doped TiO2 model. Density functional theory calculations are basically computational simulation techniques that mainly depend upon quantum mechanics Schrödinger equation. Schrödinger equation was first developed in 1926 by Schrödinger, but the problem with Schrödinger equation is that it can only be applied to a simplest simple like the hydrogen atom that only contain one electron. For most number of electrons, the Schrödinger equation solution is too much difficult. The DFT calculation is first introduced in 1964 by Walter Cohen and Hohenberg. The two basic theorem of DFT calculation is that the ground state energy from Schrödinger equation is a unique functional of the electron density, and the second theorem states that the electron density that minimize the energy of the overall functional is the true electron density. So Schrödinger equation actually have three end coordinates, but for density functional theory we reduce electron density that is a function of only three coordinates. Computational methodology. Density functional theory calculation basically depends upon three exchange correlational functions that include local density approximation, LDA functional, generalized gradient approximation, GGA functional, and hybrid functional. For the current research work, we introduced GGA functionals to the computationally designed model. For the calculation of structural properties, we employed PBE exchange correlational function, and for electronic and optical properties we employed GGA plus U Hubbard modified exchange correlational functional. For results and discussion, on the left side in figure A, the computationally designed model for pure anatase TiO2 is shown. Figure B represents the latest parameter of the TiO2 unit cell, and figure C represents the later parameter for the optimized TiO2 unit cell. On the right side, we designed a 2x2x1 supercell model for anatase TiO2 along with latest parameter for this supercell. The left hand side, in this figure a computational model of pure anatase TiO2 primitive unit cell is shown along with optimized latest parameter, and for the right hand side, the figure include the computational model of pure anatase TiO2 unit cell in reciprocal space. These are the computational model for 2x2x1 anatase TiO2 supercell with 2.0 atomic percent of carbon doping, and the figure B is for 4.17 atomic percent concentration. Band structure plots for pure TiO2 and carbon doped TiO2 is also shown here. This figure A represents the band structure plot for TiO2. The blue states represent valence bands, and the green represents the conduction band. The red dashed line represents the Fermi energy level. The band gap energy is 3.13 for pure TiO2, and for the carbon doped TiO2 model it is reduced to 2.52 electron volt. These are the density of states plots for the pure and carbon doped TiO2 model. For the pure TiO2 there are no carbon impurity states, but for carbon doped TiO2 model the impurity states of carbon were introduced, is displayed in this dashed line. The band gap was also reduced from 3.13 to 2.52 electron volt for carbon doped TiO2. The density of states results also confirm the band structure results. The optical absorption plot for undoped and carbon doped TiO2 is also shown here in this figure. For the pure TiO2 model, the optical absorption is around 380 nanometer, that is extended to 450 nanometer for the carbon doped TiO2 sample due to the reduction of the band gap energy from 3.13 electron volt to 2.52 electron volt. Conclusion. In this work, the effect of carbon doping concentration on the structural, electronic, and optical properties of anatase TiO2 was studied using density functional theory calculation. The main finding of this research work is that a significant band gap reduction was observed for for the addition of carbon impurity atoms to the TiO2. New impurity energy states were introduced in the band structure of TiO2, is confirmed by density of state plots. Moreover, increasing the carbon concentration more effectively narrowing the band gap of anatase TiO2. That is also mentioned that as we increase the concentration from 2.08 to 4.17% of carbon doping, the band gap energy is reduced from 3.13 electron volt to 2.52 electron volt. A band gap reduction causes the redshift of the optical absorption age and thus improving the visible light absorption. Also increasing the optical absorption in the visible range enhance photocatalytic activity of TiO2. So carbon doping of TiO2 with a proper mechanism is a feasible method to improve the photocatalytic performance of TiO2. These are the references for our article. For financial supports, we are thankful to Ministry of Higher Education Malaysia, MOHI, University Technology Petronas, UTP, and for lab facilities, we are thankful to Center of Innovative Nanostructure and Nanodevices, QUINE, and Fundamental and Applied Science Department, UTP. Thank you all for being here.
Okay. Thank you, Mr. Faman. So,
Thank you, sir.
yeah. So, so far, there's no question. So, thank you again for your
Yeah,
presentation.
yeah.
Okay, let's proceed with the next presenter. Oh, okay. Actually, okay, Mr. Farman, you have a question from Mr. Faisal. So, his question is, have you validated your theoretical findings by using experiment?
Yes, later we validate the experimental results, and the findings were the same as was predicted by the theoretical results.
Okay, so it's already validated. All right.
Yes,
Thank you,
yeah.
Mr. Farman.
You're welcome, sir.
Okay, let's welcome another presenter, but I'm not sure whether he's already. Okay, I would like to welcome Miss Camila Ramli from UTP, and her title of presentation is Effect of Addition of Low Loading of Graphene Oxide to the Physical Characterization of Electrospun Polystyrene Fiber Mat. So welcome, Miss Camila Ramli.
Good days, ladies and gentlemen. Thank you for all ESCON 2020 committee for the utmost effort to conduct a virtual conference despite the pandemic. My name is Kamila Binti Ramli from University Technology Petronas, and I would like to present my research entitled Effect on the Addition of Low Loading of Graphene Oxide to the Physical and Characterization of Electrospun Polystyrene Fiber Mat. The presentation will cover on the introduction, where the fundamental of the electrospinning is discussed, methodology, results and discussion to show there is some improvement in the mechanical properties, even though only a small loading of graphene oxide was added. And last but not least, the conclusion. In recent years, highly flexible material has gained attention due to its potential to be more portable and wearable. What is more important, a flexible fiber mat can have a roll-to-roll application, so it will be much easier to be applied on any surfaces. Nanofiber mat is usually used in drug delivery, bone or skin tissue engineering, energy harvesting, and energy storage. Electrospinning method is very popular to produce fiber mat because the diameter, porosity, and the alignment can be intricately tuned. Typically, an electrospinning consists of two electrodes. One is the needle and another one is the collector. Initially, the drop of polymer solution injected by the syringe at the tip of the needle was spherical in shape due to its surface tension. When voltage is applied, electrostatic force will overcome the surface tension, transforming the spherical shape into an oval shape and finally deform into a conical shape called Taylor cone. Further increment of electrostatic force will pull the polymer solution drop and produce jet solution, which will be grounded onto the surface of the collector. The morphology of the fiber is highly dependent on the electrospinning parameter. Hence, processing must be controlled in order to eliminate morphological variations and the reproducible formation of the desired structures. Apart from having high thermal and chemical resistance, electrospinning of polystyrene alone is prone to low mechanical strength and challenging to be processed when it is subjected to the specific application that requires high durability of the membrane. For this reason, fillers were added to the wet electrospinning in order to counter the drawback of low mechanical strength of single electrospun fiber. The advantages of wet electrospinning over melt electrospinning is polymer with high melting point can stay in liquid form at room temperature. It can reduce the potential of polymer to undergo chemical reaction when it is applied under high temperature, and physical blending of filler either miscible or immiscible can be electrospun using wet electrospinning. Hence, the objective of the research is to study the impact of low loading of graphene oxide embedded within the polystyrene fiber. For a start, For a start, polystyrene solution was prepared in 20% weight over volume in dimethyl formamide. It is stirred for 12 hours to promote homogeneous mixture. Graphene oxide in water dispersion were dried at 80 degrees Celsius for 12 hours to eliminate water content in graphene prior to the electrospinning process. Afterwards, 0.01% of graphene oxide were added to polystyrene solution and sonicated for 1 hour to promote homogeneous dispersion. The PS solution, the polystyrene and graphene oxide solution were then electrospined using these parameters. The collector used is the rotating type. The distance from needle to the collector is 10 cm. The feeding rate is controlled at 1 millimeter per hour. The relative humidity is around 61% to 67%, and the temperature was 23 degrees Celsius to 26 degrees Celsius. This is how the final product of the electrospun membrane was looked like. Afterwards, this sample was subjected to FTIR, FISEM, Raman, XRD, and universal tensile machine to evaluate the effect of the addition of the graphene oxide to the polystyrene solution. The changes of the diameter of the electrospun fiber was evaluated by FISEM. It was observed that the non-bits fiber of polystyrene fiber mat diameter reduced after the graphene oxide is embedded into the fiber upon electrospinning process. The diameter of the initial polystyrene fiber mat was ranging from 2 to 5 micrometer, while after the graphene oxide addition, the size is decreased in diameter to around 1 to 3.5 micrometer. This morphology is most likely was affected by the increase in solution conductivity, causing the low surface tension at the tip of the electrospinning needle, eventually causing a thinner solution jet captured by the collector. Infrared is excellent for carbonyl C1 species, while Raman is quite variable. This band is easily identified in the IR spectrum because of its intensity and lack of interference from most other group frequencies. The carbonyl in graphene oxide can be seen at 1713, the frequency, the wave number 1713. In addition to that, the characteristic peaks of hydroxyl OH stretching at 3166 and the C double bond C also can be seen at 1586. Based on the FTIR spectra alone, the polystyrene GO absorption bands were poorly resolved since it is similar to PS spectrum, possibly because of randomly dispersed graphene oxide and very small loading of graphene oxide in the fiber mat. Additionally, it is also attributed to the physical attachment of TO that stuck in between the polystyrene chain. In contrast to FTIR spectra, Raman spectra shows the characteristic of graphene oxide in polystyrene embedded with GOMAT. The profound C double bond C showing the graphitization of carbon-based material at 1595 also can be seen at PS and GO spectrum. From the XRD result, the GO sample having prominent peak at 10.5 degree, showing the graphene oxide characteristic. PS, which is having two broad peak at 9.5 and 18.8, would decrease upon addition of GO, indicates there are dispersion of GO in polystyrene sheet. The improvement in tensile strength and elastic modulus as shown in table 1 indicates a good dispersion of GO in polystyrene polymer. It may be due to elongated pores after the addition of filler as observed as compared to the initial polystyrene fiber. The GO is suspected to increase the conductivity of the PS solution, causing it to inject faster toward the collected RAM. Hence, to conclude the presentation, based on this study, it can be concluded that profound changes could be observed in the final product of the PS-GO mat, despite of the addition of GO is considered around 0.01%. This conclusion is drawn based on the morphology obtained by FISEM and the peak of GO in the Raman spectra. By adding GO to the polymer solution, the solution conductivity is increased, causing the low surface tension at the tip of the electrospinning needle and eventually produce a thinner solution jet captured by the collector. Additionally, it was also demonstrated that the loading of graphene oxide dispersed in polystyrene fiber mat can increase the mechanical strength of the PSGO as high as 6%. Thank you for listening. I would like to open the floor for Q&A session.
Okay, thank you, Miss Camila. And apparently there's no Q&A from the audiences. So thanks again, Miss Camila, for your presentation. Thank you.
Okay, thank you, Dr. Lee.
Okay, so we would like to uh, welcome Dr. Hassan Ali for his title of presentation, Study of Dielectric Properties of SRFeO3 Nanoparticles for Enhanced Oil Recovery. Let's welcome Dr. Hassan Ali.
Thank you. Thank you, doctor. My name is. Okay. Hello, everyone. I'm Dr. Hassan Ali, and I'm a graduate from University of Technology Petronas in Malaysia. Uh, Today, I'm presenting in ESPON for the conference in International Conference on Fundamental and Applied Sciences, Icfas. And the topic of my presentation is simulation and experimental study for electromagnetic absorption in sandstone with strontium ferrite nanofluids. So I will begin my presentation with the presentation outline in which we will discuss about the enhanced oil recovery, smart nanofluid simulation for electromagnetic absorption, experimental setup, results and discussion, and at the end we will go for the conclusion. So first of all, what is the enhanced oil recovery? It is basically a technique in which we have been witnessing rapid developments in oil and gas industry, where around 70% of the oil reservoirs around the world have reached their maturity stage. So majority of the oil fields only produce a fraction of oil contained in the reservoir, but uh, around 30 to 40% of the oil which remains in place, which cannot be extracted with conventional sources or conventional techniques. So we use some unconventional techniques such as gas injection, thermal injection, chemical injection, and microbial injection. These flowcharts tell about the percentage of these techniques which are being used for the enhanced oil recovery. So when we further disintegrate this pie chart, we see that we are actually using the chemical methods, which are the nanofluids for the injection in the reservoir, which also helps in not only recovering the oil from the reservoir, but also the extending the life of the oil feeds and increase the recovery factor. So we are we will be using smart nanoparticles uh, for this enhanced oil recovery. But what are the smart and nanoparticles? First, we have the concept of magnetic nanoparticles, which are the ferrofluids in which we produce the magnetization by applying the external magnetic field, which actually aligns these domains of the nanoparticles in the direction of the in the direction of the magnetic field. So if we change the direction of the magnetic field, these domains can be the direction of the domains can be changed. So it also produces the Niels relaxation effect, which is also same that as we change the direction of the magnetic field, it changes the domain direction. Then we have some dielectric nanoparticles, including zinc oxide or aluminum oxide. And these type of nanoparticles include the effect of the electrological effects, which means that on the application of the electric field, and the particles of the dipoles that arrange themselves in a regular pattern. So okay, let me open the pointer. Okay, so these the dipoles, which are the dipoles of the molecules, they align themselves in the direction of the electric field. Then we have the smart nanoparticles, which include both the magnetic and dielectric nanoparticles, both properties of magnetic and dielectric nanoparticles. These are special type of multiferric materials, uh, which are combination of the um, electric component and the magnetic components. And on the application of the electric and magnetic field, we can see that both the effects of the polarization and magnetization in these nanoparticles. So as we know that electromagnetic field is a combination of electric and magnetic components. So we can use this electromagnetic field to change the direction of the domains and also the direction of the dipoles. So these smart nanoparticles or the nanofluids actually they change the dielectric parameters in the dielectric and magnetic parameters in the reservoir. How they change, and they actually change the polarization and magnetization properties. And at the end, when we apply when we apply some electric field, there is some increase in the absorption loss due to the internal reflection. So this absorption losses, they actually enhances the reflection and transmission coefficients, and they are responsible for the alteration of viscosity, wettability, and interfacial tension of the oil water. So therefore, we can increase the mobility of oil, because as we increase the absorption in this part, so more and more particles in this reservoir will be activated. Activation means that they will affect the interfaces of oil and wall of that reservoir, so that which can change the viscosity and wettability and interfacial tension. So in the working part, we did some simulation for electromagnetic absorption, in which sorry, in which we proposed the model, and then we had some geometry in which a two-port porous system was used, and then we have set the boundary conditions, which were the perfect electric conductor, and at the end we apply our model for the reflection loss. So this was the geometry in which on one side we placed the sample, and on the other side, when we applied some electric field on the port one, electromagnetic field actually on port one, we received and the reflection coefficient or the transmission coefficient at port two. So then we calculated the absorption in that reservoir. So these are table one, shows some parameters for which we were used in the simulations. So this is the synthesis technique for strontium ferrite particles, in which we use the strontium nitrate and the ferric nitrate solutions, and then we added these solutions at 90 degrees centigrade by adding an oxidizing agent as a catalyst. So HNO3 was the oxidizing agent, and at the end we received some SFO nanopowder or on the calcination at 500 degrees centigrade. So this is picture shows the vector network analyzer, which was used for the calculation of dielectric and magnetic properties of the samples. So there are some results for XRD, FESEM, and EDX, which shows that the XRD results show the formation of strontium ferrite peaks. Which are actually very sharp peaks, you can see, which show the high crystallinity, and when compared with the JCPDS cards, we get the exact results for strontium ferrite. And for the FESEM, we actually obtained some agglomeration and this porous-like structure of the particles, which happens due to the combustion or the partial sintering of the particles. So we can actually see some of the particles which are being attached with this uh, porous materials, but this size of the particles was some of the particles was in the nanometer range. And then at the end, we have some EDX spectra of this strontium ferrite, which shows the elemental formation of these particles. So these are the dielectric properties which were obtained from the vector network analyzer. These properties clearly show that for the first of all, we have E prime, epsilon prime, which is the dielectric permittivity, and the dielectric permittivity of this SSR particles, which is strontium ferrite particles with sandstone, are increased clearly as compared to the only the s- sorry, as compared to the sandstone only, which did not contain any particles, strontium ferrite particles. And then again, for in dielectric loss, epsilon double prime, we have again the increased activity of particles of the sandstone with the strontium ferrite as compared to the sandstone particle only. And at the end, when we calculated for the dielectric loss factor, tangent delta E, so we again get some high peak, or get some greater values for as compared to the dry sandstone at around 8.35 gigahertz frequency. So these results actually show that uh, with the inclusion of nanoparticles, or with the inclusion of the strontium nanoparticles, the dielectric properties of the material has been enhanced. So then we calculated the reflection loss parameters by the simulation, which told us that the reflection loss is for strontium fluoride is not very high. As we go down, the reflection loss gets increased, but in our case, the reflection loss for strontium fluoride is not very high. But you can see that it shows a very consistent value for all the frequencies. The reflection loss is almost the same. But for the sandstone, at some points, at some frequencies, the reflection loss is high, while at some other, the reflection loss is quite low, which tells us that um, we can use any type of frequency for enhanced oil recovery to be used for strontium ferrite particles to get absorbed in the material. So for the conclusion, our simulation results show that the reflection loss and the dry rock increases with an increase in the frequency, while the decrease of the rock with strontium ferrite nanofluid. This is due to the ions, presence of ions, the permittivity value increases, and more waves are absorbed uh, for strontium ferrite. The results from the network analyzer show that the inclusion of the particles, the dielectric permittivity of the system increases, and hence the dielectric loss decreases, which is beneficial for the effective activation of the particles and can be useful for enhanced oil recovery. So also for the dielectric loss factor is maximum for strontium ferrite as compared to dry rock and high absorption of electromagnetic waves. The strontium ferrite can be used as a potential material for enhanced oil recovery. So here are some acknowledgements and the references. Thank you so much.
Okay, thank you, Dr. Hassan Ali, for his presentation. And there's no question from the audiences. So thank you again, Dr. Hassan Ali, for his presentation. Thank you. So
Thank you, sir.
okay, so we would like to welcome the last presenter in this session, Mr. Bashir Abu Bakar, for his title of presentation, Temperature Conductivity Relationship of Solid Polymer Electrolyte Membrane Base on PBA uh, potassium carbonate. Potassium carbonate. Okay, let's welcome Mr. Bashir.
Assalamu alaikum and very good day. My name is Bashir Abu Bakr Abdul Qadir from University Technology Petronas in Malaysia. I'm here on behalf of all authors to present our paper titled Temperature Conductivity Relationship of Solid Polymer Electrolyte based on PBA potassium carbonate. First is introduction. Currently, rapid increase of fossil fuel crisis and ecological deterioration have created a lot of concern about environmental sustainability and global economy due to the limitless energy consumption of world growing population. This has indeed created a lot of concern and demand utilization of renewable energy such as wind, hydro, and other sources of energy in order to replace the hazardous fossil fuels that are being used currently. However, the use of these renewable energy sources has come with a lot of drawback, such as it cannot produce in a larger quantity or it cannot be sustained to replace the current fossil fuel. Another drawback or disadvantage of using such kind of renewable energy is a low power output. Therefore, there's a need to improve or develop another source of energy known as energy storage devices. Different energy storage has been developed worldwide, like fuel cell, batteries, capacitor, and other energy storage devices. However, among all, supercapacitor shows and has a lot of disadvantages over other energy storage devices. For example, supercapacitor was reported to have a very high power and energy density, which may improve the power output from the energy storage devices. And also, the use of supercapacitor was found that it can be used for several times without deterioration. Therefore, supercapacitor has been chosen to be one of the best candidates to be used as an energy storage devices. Moving, supercapacitor was found has three major important components, which is electrode, electrolyte, and separator. This study is mainly focused on the development of the of the electrolyte as one of the components of supercapacitor. Electrolyte has been divided or has been categorized as a solid and liquid electrolyte. Previously, the use of liquid electrolyte is dominant worldwide, and this is because of its availability. However, the use of liquid electrolyte was found to have a lot of disadvantages. For example, it can be easily leached out from the system, which may cause an explosion while in this energy storage system. Another drawback of the use in the use of liquid electrolyte is was found to contain a flammable solvent, which also has a lot of effect while during the energy output during the while the energy storage in the process or in the use. Therefore, based on these disadvantages and so many others, then the new type of electrolyte was produced as known as solid electrolyte. Solid electrolyte is a very important electrolyte because it is very safe to be used because there is no issue of leakage while in the energy storage system. Therefore, this study will focus on the development of solid polymer electrolyte from the PBA and potassium carbonate in order to improve the conductivity and the performance of the electrolyte. Now the methodology. We synthesize or develop our electrolyte from the potassium carbonate as a source of ions and the polymer or PBA as a polymer host or polymer matrix. We mix the two constituents together and then stir for some period of time until the two components, the salt and the polymer, has been completely dissolved, producing a very homogeneous and clear solution. Then we casted this solution in a petri dish where we found our electrolyte to be highly flexible and transparent material, which is ready to be used for any energy storage system. Then we move to characterize the produced electrolytes using physicochemically using the FTR in order to study the functional group between the polymer and the salt. And also we characterize the electrolytes electrochemically using electrochemical impedance spectroscopy in order to study the ionic conductivity. Now the result and discussion. We use the FTR in order to study or to examine uh, the changes between the polymer before incorporation of the salt and after the incorporation of the salt. It was reported that by blending the polymer and the salt, there will be an extra site for action and jumping of ion that make the ionic conductivity to improve. Here, as can be seen, the spectrum of the fuel PBA and potassium carbonate is shown in this particular figure. This result shows that the band of hydroxyl of PBA is seen around 32.94 per centimeter. However, after the successful incorporation of the potassium carbonate, the band has decreased from 1394 to 3266 per centimeter, replicating the physical connection between the polymer and the soil, which due to the mix of iron in the polymer matrix. The changes shown here and the shifting and enlargement of the peak intensity observed here after successful incorporation of potassium carbonate is obviously displaying the effective realization of solid polymer electrolyte from PBA and potassium carbonate, showing from the PBA and potassium carbonate composite, showing successful composite formation between the PBA and the salt, which is potassium carbonate. And then electrochemically, we also synthesize the electrolyte using electrochemical impedance spectroscopy. As can be seen here, the electrolyte after EIS analysis or electrochemical impedance spectroscopy, all the two electrolytes shows a spike in both lower and higher frequency regions, showing a double layer formation. From the impedance, from the electrochemical impedance spectroscopy from the EIS plot, we were able to extract the bulk resistance from the axis of the impedance analysis. Based on the bulk resistance, we were able to compute the ionic conductivity for the electrode at different temperature. As can be seen, ionic conductivity was found to increase with the increase in temperature until we're at the 100 degrees C, where the highest conductivity was achieved for both electrolytes. The increase with temperature, the increase in conductivity with increase in temperature may result or may be connected with the increase in the number of ion migration between the electrode and electrolyte interface, which is with the activation or with the increase of thermal activation, there's high chances of ions movement and ion jumping and hopping between the electrolyte, which may increase the conductivity. However, the further increase in temperature beyond 100 degrees C, we observe a decrease. This may lead this due to the as higher temperature there is possibility of ion, which is from the potassium carbonate K plus, which is an active ion, to be converted into the inactive ion of K, inactive ion of K from K plus of potassium ion to K0 at higher temperature. Also, the higher temperature, there is a possibility of agglomeration and crystallization of ions, which also may lead to the decrease in ionic conductivity. In conclusion, in this study, we found we solid polymer electrolyte based on PBA potassium carbonate were prepared and characterized. The structural result confirmed that potassium carbonate has successfully incorporated into the polymer matrix of PBA, which confirmed the composite formation. The addition of salt into the polymer increased the ionic conductivity significantly, as can be seen earlier, which may be linked to the increase in number of ions on the surface of the polymer. The electrolytes showed that ionic conductivity is temperature dependent, where the highest conductivity of 9.4 times 10 to minus 5 millisiemens per centimeter was achieved at 273.15 Kelvin or 100 degrees C. Therefore, we can say this study indicates that the solid polymer electrolyte based on PBA potassium carbonate can be used as a capable electrolyte for the fabrication of any energy storage device due to its higher ionic conductivity. With this, I can say thank you and assalamu alaikum.
Okay, thank you, Mr. Bashir. So, okay, there's no question came from the. So, thank you again, Mr. Bashir, for your presentation. So, I think because after this, Dr. Bashir, Mr. Bashir, we have end our session for today. So, thank you again for attending Icfas, and see you next round. Okay, see you again, hopefully. And have a great time. Okay, bye. For attending this session and hope to, okay, and goodbye.